Good afternoon. All right, so we're going to continue the review today. So we'll pick up with example 4, which is where we stopped. Before we do that, I do want to show you some of those things I was telling you about in terms of websites that'll do some of these processes for you and kind of show you steps and stuff. So I was going to point that out on 2 of the examples we'd already done just to kind of show you how that works in case you ever want to use those in the future. And then when we do the integrals later on, I'll show you some of the calculator stuff also, because that you can actually use to check yourself on the final exam if you have a graphic calculator. So that's what we'll do today. Don't forget, if you haven't already signed up for exam time, the link to do that is in the announcement section. So just make sure you go back and look through there, find that link. And again, it'll take you less than a minute because you're just putting in your email address, choosing a day, choosing a time, right? So it's real quick and easy. But once you know when you can actually take the exam next week, go ahead and do that for me, okay? I think that's all I have right now in terms of announcements. So any questions, comments, or concerns before we get started today? All right, and like I told you yesterday, right, as we're going through these, if you notice there's problems where you're like, ooh, I really want more practice of that type of problem, please let me know so that I can find more of those problems, because I think we'll have at least one extra day this week that we can actually work through additional problems in addition to the exam review if we need to, okay? All right. So like I said, what we're going to do first is I want to go back to example 1 with the limits, and I'm going to show you a website that actually will do a lot of these calculus calculations for us. So this is a good way if you're ever doing work outside of class or whatever, and you just want to check yourself, or if you get hung up on a problem and kind of need to see how to work through it, this is a really good one. Okay, so it's called Symbolab. So I'm actually going to do this first limit problem here. And I'm going to share my screen so you can see it. All right, so like I said, Symbolab, you can see the title up there in the upper left-hand corner. This will actually do a lot of things for you, okay? So in terms of derivatives, integrals, limits, a lot of different calculus stuff. You can see there's even summations there. So in this case, if you want to do a limit, you can see the one that I've got typed in there. It's the first example. You would just click on the limit here. It's going to give you x approaches infinity when you first select it. So you just have to change that x approaches to whatever you're approaching. In this case, we're going to -3. Then you'll just type in your expression just like you would, in Desmos or something like that. And then when you click go, it's actually going to do the calculation for you. So it'll give you the answer right here at the very beginning is 3/7, which is what we got yesterday. But the nice thing I like about Symbolab is it also will break down the steps for you. Now, some of these are behind a paywall, so it's not going to show you every single step unless you actually pay for it. But it will at least most of the time kind of show you how things would simplify and that kind of thing. So if you're ever stuck on how to get started on a problem, this is a good way to kind of figure out where to go, okay? So I wanted to show you that. It'll also, like I said, do derivatives, including implicit. So the other one I was going to show you was the implicit differentiation that we did yesterday. You can just select d dx, and then you can put in the entire equation that you're looking at. So like one of them we did yesterday was x cubed cosine of y plus cosine of 2y equals xy. Sorry, and this first one was supposed to be sine, not cosine, so I'll change that. All right, and so then you can just click go. And again, it's going to tell you on that very first line what the answer should be, and then it'll actually break down the steps. And you can see in this case, it shows you, what you would get when you actually apply the chain rule, the product rule, all that stuff. And then it's going to show you what that solution would be once you actually isolate your y prime or your dy dx and solve. And that's again the solution we got yesterday. And so I just wanted to point that out to you because I know I haven't used it throughout the semester. But, and again, you can't use it on tests or exams, right? But if you're doing homework and just want to check yourself, or if you're kind of stuck on a problem, that's a good place to go. Okay. All right. So any questions about Symbolab? right. All right, so like I said, we're going to get started on example 4 today. So let me get to that one. We left off. All right, so we're looking for an equation of a tangent line and a normal line to the curve at the given point this time. So if we're looking for our tangent line, first of all, what's the first thing we're going to have to find here? Good, first derivative, right? So if I want to find the first derivative of this one, what would you do first? All right, good. Let's go ahead and make that a fractional exponent. So I'm going to rewrite this now as 1 plus 4 sine of x to the 1/2 power. All right, so now we can do our y prime. So how are we going to find y prime? All right, this is going to be a chain rule, so we'll let u be the inside piece here. Let's say u equals 1 plus 4 sine of x. And so what's our u prime going to be then? Good, so this gives us 4 cosine of x. So now when we apply our chain rule, this is going to give us 1/2 u to the negative 1/2 times the derivative of u. And then when we substitute back in here, it's going to give us 1/2 times 1 plus 4 sine of x to the negative 1/2 times 4 cosine x. Okay, now, if you want to, right, you can rearrange some of this stuff, move the negative exponent to the denominator, just go ahead and put the 4 cosine x up top. So we'll have y prime equals, and then in this case, 4 times 1/2 is just going to give us 2, right? So we'll end up with 2 cosine x over 1 plus 4 sine of x to the 1/2, or if you want to write that as a square root, you could. Any questions on how I got that as my first derivative now? All right, now that we have our derivative, what do we have to do next? Okay, good. So we can plug in our values. In this case, the only thing we have in our derivative is an x. So we really only need the x value this time, right? So I'm looking right here at my ordered pair. There's my x value, so I'm going to plug in 0. So we know our slope then, because that's what the first derivative represents, is going to be 2 cosine of 0 over 1 plus 4 sine of 0 to the 1/2 power. Now, if we simplify that, okay, what's 2 times the cosine of 0 going to give us? Okay, so that's going to give us 2. And then down here now, what are we going to get? Yeah, just 1, right? Because 4 times the sine of 0, that's going to become 4 times 0. That's 0 plus 1 is 1, and the square root of 1 is still 1. We get 2 over 1, or just 2 as our slope now. So just remember, first derivative tells you the slope of your tangent line. So once we plug in that x value, that's what our slope's going to be. Once we know our slope, now what can we do? Okay, good. So we can use our point slope formula, which is y minus y1 equals m times x minus x1. We're just going to substitute what we know. So we have our slope, that's our m value. We have an x1 and a y1 up here now. We're going to get y minus 1 equals 2 times x minus 0. And honestly, if you get to that point, I'm good, right? If you want to stop right there, if you want to put it in slope-intercept form, just distribute the 2, move the 1 to the other side, and that would give us y equals 2x plus 1. Okay, so this is our tangent line. Now, don't forget, it also asks for the equation of the normal line. So how are we going to find the equation of a normal line? Okay, almost, right? So what do we have to do to the slope? Well, what do we know about normal lines and tangent lines, first of all? Okay, negative reciprocal because they are perpendicular, right? So not only do we have to take the reciprocal of that slope, we also have to make it a negative, right? So what is the slope of our normal line going to have to be this time? Negative 1/2, right? So we're going to use negative 1/2, still using the same point. So now we're going to use this formula here. We're going to get y minus 1 equals negative 1/2 x minus 0 this time. And again, you could leave it like that, or if you want to distribute here, that's just going to give us y equals negative 1/2 x plus 1. That is our normal line here. So anytime you're looking for a tangent line, just remember you're finding your first derivative, you're plugging in whatever values from your point you need to. That's going to give you the slope of your tangent line. Then we can use the point and the slope with our point slope formula to get the equation. Normal lines, though, are perpendicular to tangent lines, so take the opposite reciprocal, right? So flip it and change the sign. That's going to give you your slope that you want to use for the normal line. Any questions on that one now? All right. Example 5. So we got the top of a ladder slides down a vertical wall at a rate of 0.15 meters per second. At the moment when the bottom of the ladder is 3 meters from the wall, it slides away from the wall at a rate of 0.2 meters per second. We want to know how long that ladder is. So what should we do first? Good. Let's draw the picture, right? And so what is this picture going to look like? Okay, good. It's going to be a triangle, and specifically, it's going to be a right triangle because we have a wall and we have the floor, right, or the ground. Here's our vertical wall. Here's the ground. And then we're going to have our ladder leaning up against the wall like that. And so these form a right angle, so we do have a right triangle this time. So now let's think about what we know. Okay, so what's one thing that's given here? All right, so we know the length of one of our sides, how far it is away from the wall. So if you want to call that X, that's fine. I'm going to use B down here just because of the formula we're going to end up using. So I'm going to say my B value here is going to be 3 meters from the wall, right? Right. We also know the rate of change of the vertical and the horizontal, right? So how are we going to label those? Okay, good. Either A prime and B prime, or if you remember, all of these are going to be with respect to what when we take these derivatives? time, right? So instead of calling it A prime and B prime, I'm going to call this dA dt and dB dt. Because this is one of those related rate problems. Every derivative we're taking now is with respect to time. Okay, so what is the dA dt value going to be this time? Okay, good. 0.15 meters per second. Now, keep in mind here that this is sliding down that wall. So what do we need to do to that rate? Make it a negative, right? Because the length of that side is actually going to be getting shorter as we go through time. So this is going to be a negative 0.15. All right, and then what's our dB dt going to be this time? That one's going to be 0.2, and that one is going to be positive because as it slides away from the wall, that length is getting longer, right? So just always think about whether those lengths are getting shorter or longer. And if they're getting shorter, make it negative. If they're getting longer, make it positive. All right. Now, what formula are we going to have to use this time? Good. Pythagorean theorem, right? So a squared plus b squared equals c squared. So then what are we going to have to do with our Pythagorean theorem? Good, right? We need these rates of change, right? So we're going to take the derivative of each one. So we've got a squared is going to give us 2a, and because it's with respect to time, don't forget we need dA dt here. Plus, next term, same thing. Power rule gives us 2b, but because we're taking the derivative with respect to time, we're going to have dB dt. And on the other side, again, same thing, 2c with respect to time, dc dt. Any questions about the derivative there? Okay, now let's start substituting in what we know at this point. So if I look at this first term, I have 2 times a. Do we know what a is? No, right? So we've got to figure out what that is. So I'm going to leave it as a for now. But we do know dAdt, right? We already wrote that over there. That's going to be negative 0.15. So put that in there. Plus, now we have 2 times the b value. And since we've already taken the derivative, we're allowed to substitute that b value in there. So it's going to be 3. And then dB dt is going to be 0.2. Now let's look at the other side. We have 2 times c. Do we know our c value? No. That's actually what we're trying to find, right? We want to know the length of the ladder. So this is the thing we're trying to solve for. So we're going to have 2c. And do we know dc dt? Okay, so the length of the ladder is constant, right? So it's not going to be changing. So what would dc dt be equal to then? So not 1, 0, right? So the rate of change of the ladder is 0 because the ladder isn't changing in length, right? So if that length doesn't change, if it's constant, then its rate of change is 0. So we can say 0 for our dc dt now. Any questions on that? Now, since that rate of change is 0, that means everything on the right-hand side just becomes 0. So now we actually have an equation that only has an a value in it, so we can solve for a. So I'm just going to multiply here and get 2 times negative 0.15, that's going to give us negative 0.3a, plus 2 times 3 is 6, times 0.2 should give us 1.2. So then when we solve this, we're just going to get a by itself, move the 1.2 over. Negative 0.3a equals negative 0.12. And so what's our a value going to be this time? Good, right? Negative 1.2 divided by negative 0.3 should give us positive 4. So now I know the length of my vertical side over here. Now, keep in mind, we're still looking for how long the ladder is. So what are we going to have to do now? Good. You could recognize this as a 3, 4, 5 right triangle. And so if you do that, then we know that C equals 5 meters. Okay, and if you don't recognize it as a 3, 4, 5, then we could go back to our Pythagorean theorem, substitute the values in, and it'll still work. So 3 squared plus 4 squared equals C squared. 3 squared is 9. 4 squared is 16. That's going to give us 25. And then when we take the square root, that'll give us 5. Right, so either recognize it as a special right triangle of 3, 4, 5, or use your Pythagorean theorem to get the length of that side now. Okay, so this is our answer. That is the length of our ladder. But again, in general, whenever you see a problem like this, if you can sketch the picture, right? Then fill in everything that you know, figure out what formula you're going to need to use, and then you're going to take that derivative with respect to time. In this case, once we plug everything in, we just have to remember that anything that's constant has a rate of change of 0. So you can actually put 0 in for the rate of change of the length of the ladder. And that allows us to solve for A, which we can then use to find C. Any questions on that one? All right. Example 6. Okay, so we have a box with an open top. It's be constructed from a square piece of cardboard that's 3 feet wide by cutting out a square from each of the 4 corners. And we're going to bend up the sides to make that box. So we want to find the largest volume that such a box could have. All right, so what do you want to do first here? All right, let's sketch it out, right? So what are we going to do this time? All right, good. It's a square that's 3 feet wide by 3 feet wide, right? So I'm going to draw my square. So I know the length over here now. It's going to be 3 feet. I know the length down here. It's going to be 3 feet also. Okay, so there's our picture to start. Now what are we going to do? Okay, good. We're going to put a square in each of our corners, right? Because we're cutting out squares from each of these corners. So I'm going to use dotted lines just to represent that we're cutting out squares here. And all of these squares need to be the same size. And that way we can actually, once we cut these out, fold this up and create our box. Okay, all right, so now each of these squares, we don't know how big they're going to be, right? But I'm just going to say, well, we're cutting out a square that's X in dimension, right? Which also means that the other side of that square is going to be X. All right, so now what can we do at that point? All right, so what would be our volume formula in general? Let's start with that, right? Because that's what we're trying to find is the largest volume. So once we make this box, what's the volume formula going to be for that box? Okay, so just in general, right? So, and be careful, right? Because it's not going to form a cube necessarily. So we don't know that all of the sides of the box are going to be the same. So just in general with a box, how would you write the volume formula for a box? Length times width times height, right? So let's just start with that. So we're going to take the length times the width times the height because all of these could be different dimensions, right? We don't know that they're all going to be the same. So now I just need to think about, in terms of the variable that I've used here, the x that we're cutting out of each corner, how would I get the length, the width, and the height? Well, let's think about each one, right? So let's think about length first. Once I cut out those corners and I fold up the sides, how long is that box going to be? 3 minus 2x, right? Because it was 3 feet to begin with, but I'm taking out an x from both corners, which means I'm subtracting 2x from each side now. So the length is going to be 3 minus 2x. What's the width going to be? Also 3 minus 2x. Because again, it was 3 to begin with. I'm taking out those 2 x's from the corners. So my width is going to be 3 minus 2x. Now we need the height. Okay, so if I do this, the height is going to be x, right? Because that's how long those squares are. And so once I fold those sides up, that's how tall the box is going to be. So then I can just multiply by x. So think about your volume formula for a rectangular prism in this case, right? Because that's what we're going to have. Then think about your length, because we're taking out 2 x's from each side. Your width, same thing. And then the height becomes x once we fold up those sides. Any questions about how I got that? Okay. Now what should we do? Yeah, let's go ahead and simplify that first, right? So we'll say volume equals, I'm just going to go ahead and multiply these first two sets of parentheses together here. So that's going to give us 9. We'll have a minus 6x and a minus 6x. So that becomes minus 12x. And then negative 2x times negative 2x is a positive 4x squared. And we're still multiplying that by x. Then I can just distribute the x to all my terms here. So we'll have 9x minus 12x squared plus 4x cubed. All right, now that we know that volume formula, what do we need to do at that point? Good. Now we can take the derivative because we're trying to find the maximum volume. So if we take the first derivative here, just using your power rule, it's going to give us a 9 minus 24x plus 12x squared. Now, once we have our derivative, what are we going to do with it? Good, right? We need to set it equal to 0 because remember, once you have the derivative, it could have a min or a max wherever the derivative is equal to 0. We set this equal to 0. How are we going to solve this now? Okay, good. Go ahead and factor out the 3 first. So we'll have 3 times 3 minus 8x plus 4x squared. And so then we need to factor it further. So what are the factors going to be for what we got left there now? If you want to rearrange the terms, right, if that makes it easier, think of it as 4x squared minus 8x plus 3. So what would be our factors there? Okay. All right, so we need to get a 6 and a 2 to get the -8. I agree with that. But what does that mean the actual factors would have to be to make that happen? Good, right? So we need a 3 and a 1 for sure to get the 3 down here. Factors of 4x squared would either be 2x and 2x or 4x and 1x. In this case, though, it's going to have to be a 2x and 2x so that we get that 2x on the outside, that 6x on the inside. And in this case, both of them are going to need to be negative so that we end up with a -8x once we combine like terms. Okay. Any questions about how we got those factors now? Okay. Now, once we have our factors, now we can do what? You could, right? So if you don't see how to factor it, quadratic formula will give you the same values. And just remember, you also have access to Desmos, right? So you could just graph that and find the x-intercepts because this one's going to come out as nice values that you could get there, right? Yeah, so 1.5 and 0.5 are the right answers, right? Because we're going to set these two factors equal to 0. So 2x minus 3 equals 0. That would give us x equals 3 halves, which is 1.5. And then 2x minus 1 equals 0 would give us x equals 1 half, which is 0.5. So again, same answers you would get if you did quadratic formula. Same thing you would get if you graphed it and found the intercepts that way. Now, we need to think about if both of these answers could work, right? Could both of these actually give us the maximum value or not? So look at your two answers here. Can we use both of them? Why not? Good. If we let x equal 3 halves, remember x represents how much we're taking out from each of these corners, right? Well, if I take out 3 halves, that's 1.5 from each corner, that's going to take out 3, which means I'm taking out the whole side. Well, if I take out the whole side, I don't have a box anymore, right? So I can't use 3 halves because that's going to be way too much. I'm not going to have a box. So the only one that could potentially even work here is the 1 half. That's going to be the one that gives us our maximum this time. If you want to do a number line just to make sure, right, you could actually, choose a value like 0.25 on one side and 1 on the other side, plug it in, make sure that it actually goes from positive to negative, but in this case, that will work out. Okay, so this is what we're using, but keep in mind, we're not looking for the length that we're cutting out of the side. We want to know what now? The actual volume, right? So we've got to take that X value now, got to plug it back in and find the actual volume. I'm going to come back up here. It's going to give us 3 minus 2 times 1/2. 3 minus 2 times 1/2 times 1/2, right? Because I'm plugging back into that volume formula that we created there. Okay, so then if we simplify all of that now, what should that give us? Good, right? So 2 times 1/2 is 1, so we get 3 minus 1, which is 2. Same thing in the other one, so we have 2 times 2 is 4, and then when we multiply that by 1/2, we should get 2. Now, what are the dimensions going to be for that volume? Feet cubed, good. So just remember, volume units are always cubic, and in this case, we were looking at feet, so that's going to be 2 cubic feet is the volume. That is the maximum volume that we could get out of a box that's made like that. So just remember, that's one of those optimization problems, right, where you figure out all your picture again if you can, figure out what formula you're working with, take your derivative to find the min or the max, depending on which way you're trying to optimize, and then just make sure you've answered the question at the end. Why did we choose the 1/2? So, like I said, if we did 3 halves, right, because it could be either one of those. The problem is when you do 3 halves, if I cut out 3 halves from both of these sides here, 3 halves plus 3 halves is actually going to give us 3, right? And I know that I only have 3 feet to actually work with. So if I cut out 3 from that side, it's no longer going to make a box because I'd be cutting out the entire side at that point. And so that's why we know the only one that's going to work in this case is the 1/2, because that would actually leave enough material to actually fold up and make a box. Any other questions there? So like I said, make sure go back and review your optimization problems, because there will definitely be some type of optimization problem on the final exam. So just make sure you're familiar with all those different types. Same thing with the related rate problems. It's not necessarily going to be a right triangle type of related rate problem. So just go back and review those from that test and then also from the textbook. Okay. All right. Example 7. We want to find intervals of increase and decrease, any extreme values, the intervals of concavity, and any inflection points. All right, so what's the first thing we're going to have to do here? So if we just want to go in order, let's start with intervals of increase and decrease. What am I going to have to do to find the intervals of increase and decrease? All right, so this is one where we're going to have to do our derivative, right? And then for concavity, we're going to have to look at the second derivative. How are we going to find the first derivative this time? It is a quotient rule. Good. So in this case, I'm going to let f be the numerator, g be the denominator. So we'll say f is x minus 1, g is x squared. So then if we find our derivatives here, what's the derivative of f going to give us? So just the derivative of x minus 1. 1, good. And then our derivative for g is going to be what? 2x. Good. So now when we find f prime of x, just remember we start with our g function, so it's going to be x squared times f prime, which is 1, minus f, which is x minus 1, times g prime, 2x, all over g squared, x squared, squared. Now we need to simplify what we've got in the numerator first. F prime of x is equal to just x squared minus 2x squared plus 2x all over x to the fourth. And then combine your like terms up there. That's going to give us a negative x squared plus 2x all over x to the fourth. And now it's up to you. If you want to factor out an x and cancel one out, you could do that. We're going to get the same results regardless of how we do it, though. Okay. All right, so now that we have this, what can we do? What do we have to do with that first derivative now? Okay, good. Find your critical numbers by setting it equal to 0. Perfect. So I'm going to set this equal to 0. And remember, critical numbers could come from the numerator or the denominator, right? Because it could also be where it's undefined. I'm going to take the negative x squared plus 2x and set that equal to 0. And we also have to think about x to the fourth equals 0. All right, so now when we simplify this one, right, factor out your x. We'll have x times negative x plus 2 equals 0. Over here, that's just going to give us x equals 0. And when I set each one of these equal to 0, what's that going to give us for the other critical number? Positive 2. Good. All right, so now that we have our critical numbers, now we can do what? Good. Make your number line, right? So I'm going to make my number line here. We've got two critical numbers, 0 and 2. Remember, this is our first derivative. So now we've got to substitute some values in there to figure out where we get positives and negatives. So what value do you want to substitute for that first interval? -1 works. Okay, so again, I'm going to substitute into my first derivative down here. So we'll have -1, -1 squared plus 2 times -1 all over -1 to the fourth power. Okay, so now just think about this numerator here. If we take a -1 and square it, that's 1, but we're making it negative, so this is -1 minus 2. So is that numerator going to be a negative or a positive? Okay, so we have -1 minus 2. Is that positive or negative? It's a negative, right? So that's -3, so we get a negative up top. What about -1 to the fourth in the denominator? Positive or negative? That's a positive, right? Because anything to the fourth power, it's an even power, should be positive. So overall now, when I divide these, what are we going to get? A negative, right? Because a negative over a positive should be a negative. So we get a negative down here. Any questions about how we got that? Okay. Now, what about between 0 and 2 now? What value could we substitute this time? Okay, positive 1 works. So we'll go with -1 squared plus 2 times 1 over 1 to the fourth. So up top now, we have a -1 squared, which is going to give us a -1, plus 2. So is that going to be positive or negative this time? That's a positive. Good. And then 1 to the fourth. Again, anything to the fourth power should be a positive down here. Positive over positive is going to be positive. Good. And then our last interval here, for sake of time, I'm just going to say we're going to go with 3. Again, substitute that in. So we have -3 squared plus 2 times 3 all over 3 to the fourth. In this case, that's going to give us a -9 plus 6 in the numerator. So is that going to be positive or negative this time? That's going to be a negative. Good. 3 to the fourth is definitely positive. So overall, this one's going to be what? That's going to be a negative. All right, so let's get our increasing, decreasing, and our min or max, and then we'll stop there for the day. So increasing intervals, what would that look like this time? Good. Just 0 to 2. That's the only place we got a positive. So there's our increasing. That means the other intervals are both negative. They're going to be decreasing. So that's -infinity to 0, and then 2 to infinity. All right. Now, do we have any min or max values based off of what we see on our number line here? Okay, so at 0, it goes from negative to positive. The problem with 0, though, what's going to happen if I put 0 back into my original function? You don't get 0, you get what? Does not exist, right? Because 0 squared in the denominator gives us 0 in the denominator. This point down here is undefined. So we can't have a min or a max there because that would be undefined for the original function. What about the 2, though? What would we have at 2 now? That's going to be a maximum, right? It goes from positive to negative, increasing to decreasing. So we do have a maximum now at x equals 2. And if you want to know the actual point there, you would substitute it back in because it does ask for the value here. So we would say f of 2 is just 2 minus 1 over 2 squared. It's going to be 1 over 4. So that would be our maximum value for that function this time. So like I said, we'll stop there, and then we'll come back and finish out the second derivative with concavity and inflection points tomorrow. Let me know if you've got any questions, and again, let me know if there's any problems that you really want more practice on, so that I can start looking for those. Continue to work through the practice exam, right, because that's going to be the best way to study for the actual exam. It'll be very similar. And then again, if you need more practice problems, let me know. Okay. Don't forget also, if you haven't already signed up for an exam time, make sure you find that link in the announcements and make sure you get that done by the end of the week. Other than that, have a great afternoon, and I will see you all tomorrow.